Hello, I'm Dr. Sisser, and this is the second in our series of tapes on elementary algebra. In this tape, we will be learning how to simplify algebraic expressions. Now, in order to simplify algebraic expressions, we're going to have to review our work on exponential notation and on the distributive law. In addition to simplifying algebraic expressions, we will also learn how to translate English sentences and phrases into algebraic form. Okay, let's get started. If I want to write 3 times 3 times 3 times 3 times 3, okay, 3 taken as a factor 5 times, we have a mathematical shorthand for doing this. We write 3 to the 5th power. This means take 3 as a factor 5 times. Similarly, x cubed means x times x times x. X taken as a factor 3 times. X squared y cubed can be is the short way of writing x times x times y times y times y. X taken as a factor twice times y taken as a factor 3 times. And 2 times x times x times x plus 3 times y can be more concisely written as 2x cubed plus 3y squared. If we see minus 4 quantity squared, it means, of course, minus 4 taken as a factor twice. Minus 4 times minus 4. When you multiply two negatives, the result, of course, is positive, 16 in this case. On the other hand, if I write minus 4 squared, we ought to remember that the exponent only applies to what is to its immediate left. So over here, it applied to the minus 4 because the parentheses indicated that we wanted to group the minus and the 4 together, and this was to be raised to the 2nd power. Here, however, only the 4 is being raised to the 2nd power. So it's negative 4 times 4, or negative 16. Now what I'd like to do is have you evaluate some algebraic expressions for certain values for x, y, and z. Evaluate each of the following expressions. For x equal to minus 3, y equal to plus 2, or just 2, and z equal to minus 4. The first expression, y cubed minus z squared. Y cubed minus z squared. Now y is equal to 2. And z is equal to minus 4. Okay, now don't make the mistake of saying minus a minus 4 is plus 4. Order of operations dictates that the multiplications implied by the exponent here ought to be performed before the subtraction. So we have 2 cubed, 2 times 2 times 2, which is 8. Take away minus 4 squared. Minus 4 times minus 4, we've already seen, is plus 16. Plus 8, take away a plus 16, is the same as plus 8 adding a minus 16. And the result is, of course, minus 8. The second algebraic expression that we're going to work with is x plus y minus z. I just want to remind you that in this problem, x is equal to minus 3, y is equal to plus 2, z is equal to minus 4. X plus y minus z. X plus y minus z. It's a good idea to use the parentheses and then to substitute in the values. For x minus 3, for y plus 2, and for z minus 4. So we have here minus 3 and a plus 2. When you subtract a minus 4, that's the same as adding the opposite of minus 4, which is plus 4. Minus 3 plus 2 plus 4, or minus 3 plus 6, for an answer of plus 3. And also, let's evaluate this algebraic expression. X, y, z squared, take away the absolute value of xy. Once again, x is minus 3, y is 2, and z is minus 4. xyz squared minus the absolute value of xy. What I'm going to do is to go through this and leave space for each of the values that I have to substitute in. X, y, z squared, take away absolute value of xy. X is minus 3, y is plus 2, z is minus 4. X is minus 3, and y is plus 2. All right, minus 3 times plus 2 gives us minus 6. Minus 4 squared is plus 16. Okay, so I performed this multiplication, minus 3 times 2 to get the minus 6, and I squared the minus 4 to get the plus 16. Take away the absolute value of, now minus 3 times plus 2 is minus 6. Minus 6 times plus 16 will be minus 96. 16 times 6 is 96. Take away. The absolute value of minus 6 is plus 6. So we have minus 96, take away a plus 6, or minus 96 and a minus 6, for an answer of minus 102. Okay, let's examine how exponents work. Say we have 2 to the 4th plus 2 squared. This would mean 2 times 2 times 2 times 2 plus 2 times 2. This would give us 2 times 2, 4 times 2, 8 times 2, that's 16, plus 2 times 2, that's 4, for an answer of 20. What about 2 to the 4th times 2 squared? That would be 16 times 4, or 64. And what about 2 to the 6th power? That would be 2 times 2 times 2 times 2 times 2 times 2, which would also be 2 times 2, 4 times 2, 8 times 2, 16 times 2, 32 times 2, 64. So we notice here that 2 to the 4th times 2 squared gives us the same result as 2 to the 6th. And what we're seeing is an example of what we call the first rule of exponents. When you are multiplying, okay, two numbers, and they have the same base and different powers, we keep the base and we add the powers. So 2 to the 4th times 2 squared is 2 to the 4 plus 2, or 6th power. Okay, now don't confuse this. 2 to the 4th plus 2 squared, we see, is not the same as 2 to the 6th. But 2 to the 4th times 2 squared, that is 2 to the 6th. And it seems to make sense. This would mean that 2 should be taken as a factor 4 times. And here we would have 2 as a factor twice. So altogether we would have 2 as a factor 6 times, and we get 2 to the 6th power. So let me write down for you the first rule of exponents. In general, a to the m power times a to the n power is a to the m plus n power. If we had x cubed times x to the 4th, this would be x to the 3 plus 4, or 7th power. And that makes sense since this has x as a factor 3 times x as a factor 4 times. So altogether we have x as a factor 7 times. Okay, let's try to use this in some examples. Let's try to simplify a times a cubed times a to the 4th power. Okay, what we do is we keep the base and we add the powers. Now, please remember, when you have a by itself here, it's really a to the 1st power. So it's going to be a to the 1 plus 3 plus 4, or a to the 8th power. Okay? Remember, the problem was originally written this way. And you have to remember that you're going to be able to keep the base a and add the powers, but don't forget that when you see an a, the 1 is implied. All right, what about this? 2x squared times 3x cubed. Because of the various laws of commutativity, of multiplication, associativity, we can rearrange the factors here so that we can write the numerical constants first, 2 times 3, then the variable terms, x squared, x cubed. So we'll write the numerical factors and then the variable factors. 2 times 3, that's 6. Now, x squared times x cubed would be x to the 2 plus 3, or 5th power. So the answer here would be 6x to the 5th power. How about 3x cubed y squared times 4x y to the 4th? All right, we're going to first write the constants, 3 times 4. We're rearranging the multiplication. Now I'm going to write the variables. Usually I write the variables in alphabetical order. So I'll have the x cubed and the x term, and the y squared and the y to the 4th factors. So we have 3 times 4, that's 12. X cubed times x, remember x is really x to the 1st power. Keep the x, add the powers, 3 plus 1 is 4, so 12x to the 4th. Y squared times y to the 4th is y to the 2 plus 4, or y to the 6th power. So we have 12x to the 4th, y to the 6th. All right. What if I told you 2 cubed times 2 squared? All right. This would be 2, keep the base, add the powers, to the 3 plus 2, or 2 to the 5th power, in much the same way that x cubed times x squared would be x to the 5th power. Okay, please remember this is not 4 to the 5th power. Sometimes people get overzealous, and while they're multiplying, they can't resist multiplying the 2 times the 2 and getting 4 to the 5th power. Now that would be incorrect. We have here 2 taken as a factor 3 times, 2 taken as a factor twice, so we wind up with 2 taken as a factor 5 times, or 2 to the 5th power. Okay. We did not multiply the x's. We kept the x and we added the powers. Similarly, over here, we keep the 2 and we add the powers. All right. What about 3 times 2 cubed times 4 times 2 squared? All right. Here, everything, all the factors are constants. We have no variable factors. What I would do in this case would be to first write those constants that do not involve powers. Say 3 times 4, and then the 2 cubed and the 2 squared. So even when you just have constants, rewrite first the constants that do not have the powers, and then the ones that do have the powers, giving me 3 times 4, that's 12. 2 cubed times 2 squared, we've seen already, is 2 to the 5th power. So 12 times 2 to the 5th power, which is, by the way, not 24 to the 5th power. It's 12 times 2 to the 5th power. 2 to the 5th power is 32. And 12 times 32 is 384. All right. Now let me remind you about the distributive law. We have the fact that A times B plus C is A times B plus A times C. For example, 3 times 2 plus 4 is 3 times 2 plus 3 times 4. In other words, the 3 is to be distributed through the parentheses. 3 multiplies the 2, and then it multiplies the 4. And of course, we can check in this instance that it gives the right answer. We have over here 3 times 6, and over here we have 6 plus 12. And of course, 18 is equal to 18. So apparently, it does give us the right answer. Nobody, however, would be multiplying 3 times 2 plus 4 in this fashion. They would be multiplying it as 3 times 6. The real value of the distributive law to us in this form would be to simplify algebraic expressions. Okay, let's try. If we have, for example, 3 times x plus 2, according to the distributive law, this would be 3 times x plus 3 times 2, which is 3x plus 6. Now, what about x cubed times x to the 4th plus 3? This would be a times b plus c is a times b plus a times c. So x cubed times x to the 4th plus x cubed times 3. X cubed times x to the 4th plus x cubed times 3, giving us x to the 3 plus 4, or x to the 7th power, plus, writing the numerical constant first, 3x cubed. There's nothing wrong with x cubed times 3, but it's more common to write it as 3x cubed. X to the 7th plus 3x cubed. Okay, what about 4x cubed times 2x squared plus 3x? This would be 4x cubed times 2x squared plus 4x cubed times 3x. This can be written as 4 times 2 times x cubed times x squared plus 4 times 3 times x cubed times x, for a final answer of 4 times 2, 8, x to the 3 plus 2, fifth power, plus 4 times 3, 12, x to the 3 plus 1, fourth power. So we have 8x to the fifth plus 12x to the fourth. Of course, we would hope that eventually you would get to the point that you could go from this step to this in your head. Just go, the 4x cubed has to multiply the 2x squared, giving us 8, x to the fifth, and then multiply the 3x, giving us 12, x to the fourth. Okay, let's go back to our statement of the distributive law. We saw before that 3 times 2 plus 4 is equal to 3 times 2 plus 3 times 4. Sometimes when people are learning the distributive law, they tend to use it even when they shouldn't. If I say A times BC, this is not AB times AC. You do not distribute the A. Here, the parentheses are non-essential, and this is just A times B times C. In other words, 3 times 2 times 4 is just 3 times 2 times 4, which of course is 6 times 4, 24. Or 3 times 8, also 24. It would be incorrect to go 3 times 2 to get 6, and then multiply that by 3 times 4, which is 12. That would give you 72, which is the wrong answer. Okay? So we do not use the distributive law here. A times BC is just ABC. But A times B plus C is A times B plus A times C. All right, now what we have been doing is using the distributive law. A times B plus C is AB plus AC in this way to multiply out expressions. We can also use it in the reverse direction to help us to factor algebraic expressions. If I have 3x plus 6, right, we can write this as 3 times x plus 3 times 2. And since this is AB plus AC, we can then write this as A times B plus C. 3x plus 6, writing it as 3 times x plus 3 times 2. That is AB plus AC is equal to A times B plus C. In other words, we may factor out the 3. AB plus AC. We factor out the A and we're left with B plus C. We factor out the 3 and we're left with what remains in each term, namely the x and the 2. Okay, how about x squared plus 5x? So we want to factor that. We have a sum of two terms, and we would like to write it as a product. We see that this is x times x plus x times 5, a times b plus a times c. We can factor out the x, and we're left with x plus 5. Factor out the x, which appears in both terms, and we go x times x plus 5. And of course, we should check this by the distributive law. X times x is x squared plus x times 5, which is 5x. All right, what about 4a squared plus 6a to the 5th? So we want to factor here. We're looking for the greatest common factor between these two terms. We look first at the numerical coefficients of the terms, the 4 and the 6, and we see that they have a 2 in common. And the a squared and the a to the 5th power have an a squared in common. Then we rewrite the terms as 2a squared, which is the common factor, times what's left here, namely 2, plus 2a squared times what's left here, which is 3a cubed. Whereas this is the 4a squared plus 6a to the 5th. What we have done is rewritten this as ab plus ac, and then we can factor out the 2a squared, and we see that over here, once we take out the 2a squared, we're left here with a 2, and here a 3a cubed. So we have factored this into 2a squared times 2 plus 3a cubed. And when we multiply it out to check it, we get 4a squared plus 6a to the 5th. All right, 3x plus 2x. Let us try to factor here. We can factor out an x, which appears in both terms, and we're left with 3 plus 2, x times 5, or, as it's more commonly written, 5x. 3x plus 2x. We take out the x, we're left with 3 plus 2, or x times 5, or 5x. 3x and 2x come under the category of like terms. Okay? 3x and 2x are like terms. These are terms that have exactly the same variable part. Okay? If we think of a term as being composed of a numerical part and a variable part, okay? In this case, the numerical part is 3, the variable part is x. The numerical part is 2, the variable part is x. When the variable parts are the same, we can combine like terms because, according to distributive law, we could pull out the common variable part and we could add the numerical coefficients. To add like terms, we combine the numerical coefficients and put it before the common variable part. So 3x plus 2x gives us 5x. And it can be done without first using the distributive law. Let's try another example. 4x squared y plus 3x squared y. We are adding two terms. They have the same variable part, namely x squared y. To add the like terms, we combine the numerical coefficients. 4 of these plus 3 of these gives us 7 of these, 7x squared y. All right. What about 3ab plus 4ba? Now, first time you're looking at this, you might say, wait a minute, these are not the same variable parts because this is AB, this is BA. But of course, we can rewrite this as 3AB plus 4AB since multiplication is commutative. And now we do see that these are, in fact, like terms. They have the same variable part. And to add them, we will combine the numerical coefficients to get 7AB. Okay, let's simplify this expression. 3a squared b plus 2ab squared plus 5a squared b minus 6ab squared. It is certainly to your advantage to rewrite your terms so that the numerical coefficient precedes the variables, and the variables are written in alphabetical order so that you will be able to recognize, for example, an a squared b and a ba squared as being really the same variable part. All right, let's see if we have any like terms. We have a 3a squared b, and we have a 5a squared b. So let me write the like terms next to each other. And a 2ab squared, take away a 6ab b squared. So we have two pairs of like terms. 3a squared b and 5a squared b gives us 8a squared b after we combine the numerical coefficients. And the 2ab squared minus 6ab squared gives us 2 minus 6, or minus 4ab squared. So we get 8a squared b minus 4ab squared. Now, frequently, we have to eliminate parentheses before we can combine like terms, like we have in the following example. 2 times 3x plus 4y plus 6 times x plus 2y. All right? Before we can combine like terms, we have to perform these multiplications. We have to distribute the 2 through the parentheses and the 6 through that parentheses. 2 times 3x gives us 6x, plus 2 times 4y gives us 8y. 6x plus 8y. Don't write 6x plus 4y. Don't forget the 2 has to multiply each term in the parentheses. Plus 6x plus 12y. The 6 multiplies the x and also the 2y. So then we can see we have 6x plus 6x plus 8y plus 12y for a total of 6 and 6, 12x, and 8 and 12, 20y. All right. How about 5 times x minus 3y minus 2 times x minus 4y? We'll distribute the 5 through the first parentheses, 5x, and then 5 times the minus 3y minus 15y. Here, think of this as adding a minus 2, which is to be distributed through the second parentheses. So we are distributing the minus 2 through the parentheses, minus 2 times the x, minus 2 times the minus 4y is plus 8y. We have now 5x minus 2x minus 15y plus 8y. And hopefully you'll be able to eliminate this step very shortly. 5x minus 2x gives us 3x, minus 15y plus 8y, minus 15 plus 8, minus 7y. So we get 3x minus 7y as our answer. All right, what about this example? 6y times y squared minus 2 minus 3 times y cubed minus 4y. We have here 6y times y squared, which is 6y cubed, minus 6y times 2, which is minus 12y. 6y cubed, and then the minus 12y. And now distribute the minus 3 through the second parentheses, minus 3y cubed, and then minus 3 times minus 4y is plus 12y. So we have 6y cubed and minus 3y cubed combines to 3y cubed. The minus 12y and the plus 12y combine to 0y, and they cancel each other out. So we just get an answer of 3y cubed. Okay. What about 8x minus 5x minus 4? Okay, the only difference between this example and this example is that there does not appear to be a number before the parentheses. When you just see a minus sign like that, think of it as a minus 1 that has to be distributed through the parentheses. So we would have 8x minus 1 times 5x is minus 5x. Minus 1 times minus 4 is plus 4. 8x minus 5x gives us 3x, and then plus 4. So we see that the minus sign preceding the parentheses has the effect of changing the signs of every term in the parentheses. So minus 5x and then the plus 4, because it has the effect of multiplying by minus 1. So for example, in general, we have minus x plus y. This means minus 1 times x plus y, or minus x minus y. It changes the sign of every term in the parentheses. All right, what about this? 14a minus 4 times 2a minus 3 minus minus, in parentheses, 5a plus 4. Okay, we have here 14a. We distribute the minus 4 through the first parentheses here. Minus 4 times 2a, it's minus 8a. Minus 4 times minus 3 is plus 12. Here, we distribute the minus sign through the parentheses, or minus 1 through the parentheses, changing the signs of each of the terms. So we have minus 5a minus 4. 14a minus 8a minus 5a. That's 14a minus 13a, which is just a, and 12 minus 4 gives us a plus 8. So we have a plus 8. All right, let's try to simplify this expression. 10x minus 2 times brackets 6 minus, in parentheses, 3 minus x. All right. Using order of operations, we're going to work from the innermost grouping symbols out. So I'm just going to leave this as 10x minus 2, 6. Now, the innermost parentheses, we're going to distribute the minus sign, or a minus 1, through these parentheses, giving us minus 1 times 3, minus 3, minus 1 times minus x, plus x. 10x minus 2. Now let's clean up what's in the brackets. 6 minus 3 plus x gives us 3 plus x. 6 minus 3 gives us a 3. 10x, now we'll distribute the minus 2 through the brackets. So it's plus minus 2 times 3, which is minus 6, and plus a minus 2 times x, which is minus 2x. Minus 6 minus 2x. And now combining like terms, 10x minus 2x gives us 8x, and we have 8x minus 6 as our answer. Okay, I'd like to spend some time with you now translating English phrases and sentences into algebraic form. I will write down a phrase or sentence in English, and we will try to then write it in terms of algebra. 8 more than a number. Okay, if we call, in these examples, x the number, let x equal the number in question, 8 more than a number x. This can be written as x plus 8. 8 more than the number x. 8 more than x, x plus 8. How about this? A number increased by 8. A number increased by 8. The number we're designating by x. The number increased by 8. Okay, 8 more than a number, and a number increased by 8, we see we can write the same way. Some of the problem that people encounter in algebra is that they can't understand how you can change the English and the algebraic form remains the same. Okay, because the basic idea is the same here. 8 more than this number is the same as the number increased by 8. How about this? A number decreased by 8. The number is x. X decreased by 8 is written x minus 8. A number decreased by 8. Increased by 8 translates to plus 8. X plus 8. A number decreased by 8 translates to minus 8. 8 less than a number. Eight less than a number is also written x minus 8. 8 less than the number x, or the number decreased by 8. So once again, we see two different English phrases giving rise to the same algebraic expression. X less than 8. X, a number x less than 8, is written 8 minus x. Look over here. 8 less than a number was the number minus 8. X less than the number 8, x was taken away from the 8. All right, each of these English phrases translated into an algebraic expression. Very often, an English sentence translates into an algebraic equation in which there is an equal sign. Let's try one of those. "18 is 3 more than a number." Here we have a complete sentence, and the is going to translate into the equal sign. "18 is equals 3 more than a number. 3 more than a number x. X is the number. 3 more than the number x is written this way. 18 is or equals 3 more than the number x. How about this? 4 times a number is 6 more than twice a number. 4 times a number is 6 more than twice a number. 4 times a number is written as 4 times x. 4 times x is, there is your equal sign, 6 more than twice the number. 4 times a number equals 6 more than twice the number. And this brings us to the end of our tape.